Hi, my name is Luke Desitels. Today I'm presenting Kobold, Evaluating Decentralized Access Control for Remote NSXPC Methods on iOS. I'd like to make a clarification about my affiliation. This work was done for North Carolina State University. I happened to be working for Samsung Research America at the time the paper was submitted, and I'd like to thank my current employer, TikTok, for sponsoring my registration. The problem Kobold seeks to solve is malware running on iOS devices that can elevate its privileges by breaking through access control mechanisms. One example would be the Pegasus spyware. This was a malware discovered in 2016. It used a combination of 3 vulnerabilities to elevate its privileges and to eventually jailbreak the device. Once the device was jailbroken, it could be turned into a full surveillance device, and brokers are willing to pay very large amounts of money for these sorts of vulnerabilities. If we are able to analyze and harden the attack surface, then these sorts of remote jailbreak attacks become much more difficult to perform. For background and to understand the state of the art of iOS analysis, I'll go over some of our past papers that Kobold utilizes. First, we worked on SandScout. SandScout reverse engineers and analyzes the iOS sandbox profile, which controls all of the system calls that a third-party application can make. However, SandScout mostly focused on just file access. It was interested in seeing, are there files that a third-party app can read and write that it really shouldn't have access to? The next paper expanded our scope not just to third-party apps, but also to system daemons. Were there system daemons that had access to files that they should not have had access to? And it also incorporated things like Unix permissions, which are the read, write, execute bits you might see on certain systems. Unfortunately, SandScout and iOracle did not consider inter-process communication. And because inter-process communication can be used for certain attacks like confused deputy attacks, it's an important part of the attack surface to consider, especially for third-party applications. Kobold seeks to fill this gap. So Kobold uses a combination of knowledge of the sandbox profile and the entitlement requirements that daemons might require in order for third-party applications to communicate with them. And it helps us to determine the attack surface available to third-party applications. One of the problems we need to solve is determining which entitlements are available to third-party applications. And at this point, I'll define what an entitlement is. It's basically a privilege embedded in an app signature. It's very similar to Android permissions, if you're familiar with those already. We also need to know which NSXPC methods are accessible to third-party apps. NSXPC is an object-oriented level inter-process communication mechanism. And some of these NSXPC methods will require entitlements in order for them to be run. By being object-oriented, it was very amenable to reverse engineering because at the higher level of abstraction provided more patterns that we could detect during our static analysis especially. Of the accessible NSXPC methods, we'd like to know which ones are dangerous and which ones can be exploited and might have incorrectly configured access control. Here's an overview of how NSXPC access control works. There's going to be enforcement in 3 different places. First, enforcement can occur at the sandbox level when the system call is made to perform what's called a mock lookup. We'd be looking up what's called a port. And here at the bottom, we have a definition of what a mock port is. It's basically the way that 2 different processes on an iOS device are able to communicate. I'm not going to go too deep into the details here, but it's important to know that they communicate using a mock port. And when the mock port on the daemon side is receiving information, it has the opportunity to check for an entitlement at the port level, or it can check for an entitlement for any of the remote methods that can be accessed through that port. So you might get a message coming in on the port, and then that message can be routed to the proper remote method that needs to execute it. And the entitlement check can occur in either of these places. Here's an example of what the policy looks like within the sandbox. Here we have some sandbox profile language suggesting that you can do a mock lookup for the vocabulary updates port if you have the developer.siri entitlement. Within the daemon, it can also have conditions and be checking for specific entitlements. So in this case, we have some pseudocode here. The daemon might be interested in an entitlement with the key of health stats, and entitlements are key value pairs. So you've got a key that maps to a value, just like a dictionary used in some languages. So the key would be health stats in this case, and we want the client to have the weight value associated with that. And the client is the third-party app who's calling the daemon. The daemon will run a check to see what entitlements the client has, and if it has the correct one, in this case, the health stats weight entitlement, it's going to send the weight back to the client. If it doesn't have it, it can throw an error if it wants to, and say there's a missing entitlement. It might even say exactly which entitlement it wants. We have to deal with 3 challenges when doing this research. First, Apple doesn't normally want third-party apps directly invoking these IPC mechanisms, so they're not clearly documented most of the time. We also need to consider the sandbox policy, which again is proprietary, has to be reverse engineered. We also need to consider these daemon policies that are coded directly into the daemons themselves. And those are very hard to reverse engineer statically. In fact, we dealt with that problem through dynamic analysis, and I'll describe that in more detail soon. Finally, we don't have a ground truth. We can't just bring our results to Apple and say, how close did we get? What we have to do instead is look for vulnerabilities that suggest we really are effectively exploring an unexplored attack surface. The first step is static analysis. We want to generate a unique ID for each remote method call that we're going to make. And our goal is to have thousands of remote method invocations in our test program. And once we're able to generate all of that code, we're going to call all of them and see what happens during dynamic testing. In order to generate all of this code, we want to go through each daemon that's offering the methods we're interested in, enumerate the ports for that daemon, so basically extract the mock ports that it offers, determine which of those mock ports are going to be accessible to a third-party app through the sandbox. That way we save a lot of time. We don't want to be testing at ports that the sandbox isn't going to let us communicate with anyway. For every method offered by that daemon, we also want to make a call for that method. And then we'll build our invocation now that we know the daemon, the port, the method, and we generate a unique call ID to help us with debugging. We're able to move on to the next one and we generate another invocation. So again, our goal is to have a very large program that's going to make several thousand of these invocations with automatically generated code. We have to make a lot of associations here, though. We need to be able to map the ports to daemons, and we need to be able to map the methods to ports, hopefully. So let's go through this one step at a time. We were able to identify all the daemons we wanted by extracting them from the iOS firmware image. This is basically the over-the-air update firmware that gets deployed by Apple. The first step is to map the ports to daemons, which we're able to do because of port pre-registration. These daemons have an incentive to have a static file, and it's a configuration built into the firmware that says, these are the ports I will be running. Don't let anybody else come up before me and try to register the same port, because that person is an impersonator. And this security mechanism makes it easier for us to do static analysis and determine what the ports are going to be without having to run these daemons dynamically. The next step is mapping the methods to daemons. For this technique, we're able to take advantage of the fact that NSXPC uses object-oriented levels of abstraction, and that helped us to be able to identify the methods within these daemons. However, we have not mapped the method to the actual port in the daemon. We don't know the association here. So in cases where there's only one port, it's easy. We just assume that those methods belong to that port. However, when there's more than one port, we make an over approximation. We will duplicate the methods across each port, and when we run this dynamically, we're able to triage out the ones that failed. And I'll show that step soon with another illustration, but for now, we've got a lot of redundant methods in our auto-generated code. Now we're ready to run dynamic analysis. And our goal here is to, like I said before, we're going to identify the method to port combinations that are not valid. And we're also hoping that there are going to be some errors returned that might say, you need this specific entitlement to do this. And in other cases, something interesting might happen. We'll call the IPC successfully, and we might be able to see what the function is because it returns data or causes some system change. One of the first obstacles that we ran into was a compile time security enforcement. We need to use the init with mock service name NSXP API, but when we try to include that in our code, Xcode throws an error, and it's basically saying you can't do this. Third-party apps are not allowed to directly invoke NSXPC. But upon investigating where this error was coming from, we found a header file, and in that header file, this is a simplified abbreviation of the function, but for the function we needed to call, it was associated with several tags: iOS prohibited, tvOS prohibited, watchOS prohibited. The way that we were able to bypass this compile time check was by basically just modifying this environment. We removed the tags that were causing trouble. We saved the header file again, and then we tried again in Xcode, and it succeeded. That's basically how it went. When running the code, we're able to first identify the port and method mappings that don't seem to work at all. And we can focus on the ones that seem to be providing good results. For each method, sometimes they don't return anything useful, but sometimes they return an error that will require a very specific entitlement. They could cause a crash, and we're able to look into those with the different crash logs on the iPhone. By the way, all of this is running on an iPhone at this point. We've compiled it with Xcode, and we just have an app on the iPhone. We run it, and we've got a bunch of logs and analysis that are monitoring what's going on. One of the methods, or actually two, are causing bells to ring. So we'd hear this very encouraging, like ding ding sound as we're rotating through all these different methods. And a few of these return data. Sometimes we had to go in and maybe decode some base64, do some manual analysis of the data that was coming back. So overall, what did we find? Well, we generated about 3,000 total invocations, but like I said, a lot of these were redundant. Only 1,500 of the methods were actually unique. Of these methods, 677 had completion handlers. A completion handler is a bit of code that you tell the system to run when the remote method is finished. And it could run even if the remote method is rejecting you and throwing an error. It'll still run the completion handler and say, hey, this is the error that came back. So there were 224 completion confirmations. These are remote invocations that the daemon actually processed and was able to send back a confirmation. I got your request, and here's what happened. 139 of these did not seem to require entitlements. The others did seem to require an entitlement, and they would either specify exactly what they wanted, or it would just say missing entitlement. While performing these tests, like I said, there were some that were actually making noise on the system, literal noise that we could hear. Others were providing information coming back, and we're able to look into a few different effects that led us to some interesting vulnerabilities. Apple granted us 3 CVEs. They've patched all of these. And we also had very many daemon crashes, but we didn't go as far as exploiting the crashes. We just reported what we saw to Apple. But we weren't trying to look for ways to do memory corruption or take it any further than just causing a crash. The first vulnerability seems to activate mobile device management functionality, even if the device has never been enrolled for MDM. In this case, we're able to block all of the websites. It affected multiple browsers, not just Safari. And if the user actually tried to tap the allow website button, they would get this scary looking PIN requirement. And we have no idea what the PIN code was because we didn't set it. It must be some default. And so it's kind of alarming to get rid of this or to try to work around it. And again, these are things that third-party apps can do that they should not be able to do. The next one was starting a dictation session without any interaction from the user. Like I said, there were bells ringing. We noticed that if you put the phone on silent, it didn't stop the bells from ringing. So that was one clue. Another one was when we found the name of the method that seemed to be causing this. It was associated with the dictation port, and the method was called start recording for pending dictation. We suspect that this is exactly the same thing that happens when you hit the microphone button on your keyboard, and it offers up dictation so that you can speak to your keyboard and it'll type out the words for you as you're speaking. In that case, we're not able to directly access the recording itself. We're able to wake up the microphone and get it working for about a second before it gives up. But it's not that we could spy on users directly with this vulnerability. We're just activating the microphone. The third vulnerability is related to the file provider, file name inference. For context, it's important to understand that there's an interesting trait in iOS where if you try to access a file with a certain call, you'll get one of two errors back that give away some information. It'll say you don't have permission to view this file, or it'll say this file does not exist. There is no such file. Because of that, if you know the file path for a file, you can infer whether it's on the phone or not by just checking that file and seeing which error you get back yet. And some files can be sensitive if they're there at all. You could have maybe system cookies or something with a specific name that you're looking for. Normally, you can't exploit this directly because the files have very long, complicated file paths, but the vulnerability provided part of the file path we needed to be able to do this. In summary, NSXPC can be exploited by malicious applications, and using Kobold, we extracted the NSXPC attack surface and we identified the vulnerabilities that I discussed, as well as a few other findings that you can find in the paper. With that, I'm very happy to take any questions that you might have.